Hello and welcome to another video. In this video we're going to be working on build a matrix with conditions. And in this one you're giving a positive integer k and you're also given row conditions and column conditions. And so the idea here is for the row and column conditions you're going to have a bunch of arrays of numbers, and these array means for the row the number that comes first, so like 1 has to come before 2 and it has to come above the 2. And then 3 has to be above the 2 as well. So like for this example, 1, 3 above 2, and 1 above 2. And for the column conditions, it's left to right. So 2 has to be to the left of 1, and 3 to the left of 2. And you're basically asked to just give any matrix that meets these things. So you can have a bunch of these conditions, and you're asked to give a matrix that meets these conditions, or some won't be possible. So in this case, there's a few that are possible. So if we have a 3 by 3, so we know that 3 has to be above 2 and 1 has to be above 2. So there's a bunch that are possible. But basically, let's say we have like 3, 2. Actually, let's see. Yeah, so I guess we could put 3 up here, and then we could put either, so we can kind of do this or another way. So we can also do the other way. So we can say, let's put 1 above 2, and let's put, I thought there were more possibilities than there are, but let's put 1 above 2, let's put 3 above 2, and then also you have to keep in mind that 2 has to be to the left of 1, and 3 has to be to the left of 2. So 1 has to be last. So it's actually going to be like this. 1 can go here. 1 has to be last, sorry. So 1 is actually going to go over here. Yeah, so 1 over here, 3 over here. But essentially there's a bunch of different possibilities. Okay, so I think this one works, right? So 3 above 2, 1 above 2, 2 to the left of 1, and 3 to the left of 2. Yeah. But the basic thing you can recognize here is actually the row and the column stuff is independent. So it's a lot easier than you think. So what we can do is, let's go back to this example. We can just have for a row and a column like some order that works. We just need one. So for the row, for example, if 3 is above 2 and 1 is above 2, that means something like this works: 3 1 2 or 1 3 2 or anything that works, right? You just need a possible solution, and then you can build a matrix. So if this is one possible row order, 3 1 2, and for the column order, I think there's only one. So it has to be, well, actually, no, it doesn't, right? It either has to be like 3 2 1. 3 2 1. 3 left. Actually, no. I think this one does have to have an exact, yeah. Because 3 has to be to the left of 2, and 2 has to be to the left of 1. So it has to be 3 2 1. Yeah, it has to be in this order. Okay, but whatever. All you need is 1. And then it's pretty easy to build a matrix once you have this, because all you have to do is say like, okay, this is my row order and this is my column order. So I know that 3 will go in row 1. And what column is 3 in? 3 is in column 0. So I'm going to put, sorry, 3 will go in row 0, and then it's also in column 0. So I'm going to put 3 here. Then 1 will go in the second row, and it is in the last column. So 1 will go here. And then 2 is in the last row, and it's in the middle column. So it's going to go here. So basically, once you have a valid like row sequence and a valid column sequence, all you have to do is just, you can put every number in a separate row, and then you look like what column does it need to be in to also match the column. So the whole thing to this problem is just, how do I get like a valid sequence of a row and column? And similarly, for the second example, so I think the row doesn't work because 1 has to be before 2. And 2 has to be before 3, but 3 has to be before 1, so that's not possible, right? So what you actually notice here is if you draw this in a graph, so 1, let's just draw a graph of like a path showing a number has to be before another one. Now 2 has to be before 3. Now 3 has to be before 1. So this is kind of like, I don't know if you've done like the course schedule or any kind of those problems, but essentially whenever you have a graph like this, where like if there's an edge, it means you have to do something before something else. Whenever you have a cycle, it's not possible, because like you can't pick to do anything here, because the only things you can pick to do are things that you've done everything before, right? So like if we pick 1, we can't pick 1 because we have to do 3 first. We can't pick 3 first because we have to do 2 first. We can't pick 2 first because we have to pick 1. So basically the only graph that you can pick stuff for is a graph that has edges. I'm just going to draw some arbitrary edges. Or not edges, that have nodes with no edges going to them. So something like this, let's say, and maybe this goes here, this goes here, something like this, right? And then maybe both of these are a requirement for this guy. So for example, for a graph like this, it means like these two have no requirements, so you can do these in any order. So maybe I'll go like 1, 2 here. Then after you do those two, these edges disappear. So now you could do these two in any order. So maybe like 3, 4. Or you could do some other stuff, right? Like you could, for example, do like 1 and then 2 and then 3 and then 4. But as long as you can basically pick a node as long as you've done the stuff before it. So one valid solution will be like 1, 2, 3, 4, 5, for example. But basically, what we can do is for the row and the column, we can turn this into a graph, and then we could do a topological sort on that to try to get a valid sequence. And a topological sort, all it does is the main idea. So for example, if you have this 1, like this example here, go to 2 and 3, go to 2. All it does is you start picking nodes that have no parents, that have no edges coming to them, and then you put them in your sequence that you're picking. And then once you pick the node, you can delete the edge. So for example, if I say like, okay, my sequence is going to be like something here. So maybe I'll pick 1 first. So if I pick 1, now this edge disappears. And I still have to pick 3 because I can't pick 2 because 2 is an edge. So maybe I'll pick 3 because it's the only one I can. And then all I have left is 2. So that's kind of the idea. So you can do a topological sort. And a topological sort, if you have a cycle, so that other example, if I go back, if you have something like this, actually, this wouldn't be a cycle. A cycle would be like this. So if you have a cycle, then the topological sort starts with nodes that have no edges coming into them. And the way to do that is for every single node, you can just count the number of in degrees. So whenever you have an edge going to a node, you will just increment its number of in degrees in an array or a hash map or something. And then you're going to do a BFS or any kind of, it doesn't really matter which way, because you're not trying to find like the best path. You're just trying to find, is there a path at all? So you're basically going to pick nodes that have no in degrees, put them in an array, and then start taking nodes out of there. And as you're taking nodes out of there, you're going to delete edges and then lower the amount of in degrees for your other nodes. And then when those nodes have 0 in degrees, then you can pick those nodes. So essentially it'll basically tell you like, is there a possible way to sort these numbers where it fits these conditions? And if you can do it for the rows and the columns, then like I said, it's pretty easy to have a solution. Because all you do is, if your row order is like I said, 1, 2, 3, then you're going to say, okay, 1 will be in row 0, 2 will be in row 1, 3 will be in row 2. And then you look at your column order. So if it's like 3, 2, 1, then you know that for 1, it will be in the last column. For 2, it will be in the middle column. For 3, it'll be in the first column. So these are independent. That's the key. So that's why it's pretty easy. So we're just going to have one number per row. And then the number per row is going to depend on both of these. And so you basically have to do a topological sort on this row conditions and the column conditions. And then you have to look, did I get something valid? And the way to test if there's something valid is you're basically going to do a BFS. And if you did get something valid, you're going to have every single node. So this should be length k, and this should be length k if you got every single node. And we're going to make a graph, and some nodes won't have any of these. So for those nodes, we're just going to make a graph with an empty list of children, and I'll kind of show you there. So it's a lot of code, but basically, yeah, you have to look at, if you haven't done topological sort, I'd recommend that, because here you're doing a couple. So I'd recommend doing, I think there's like a course schedule problem, and you can do that one. But that's the basic idea. So you do a topological sort, you get a valid row sequence, you get a valid column sequence, and from there it's really easy to build a matrix because the row of your item will be here, the column will be here, and to efficiently, to not have to like do in k by k, even though I think you can, it doesn't matter, right? We can just turn this into a hash map. So for this, we're gonna say like 3 is at column 0, 2 is at column 1, 1's at column 2. But you can also do an n squared, and that'll also pass. So you're just going to go through all of these, and you're going to say like, okay, this is row 0. Where is it in the column? It's in column 2. This is row 1. Where is it in the column? It's in column 1. This is row 2. Where is it in the column? It's column 0. All right, so we have our row graph, which is a hash map, and then we have our column graph, which is a hash map. And I use a set instead of an array list for the edges, because you do have duplicate edges. So yeah, like here they have duplicate edges, so that'll just save you some space. And then you have your in degrees for the rows and the columns, and then basically I ended up putting every single number 1 through k. You can probably make this more efficient by not putting in every single number 1 through k to just use less space. Theoretically, if the row conditions and the column conditions do include every number, like worst case it'll be the same, but ideally you can make it a little bit better in practice. Yeah, and then basically for every single edge, you add the edge to the graph, and then you also increment the in degrees of whatever edge you're going to. And this is 1 indexed, or the in degrees are 0 indexed, but the nodes are 1 indexed. It's 1 through k, but this is 0 to k minus 1, so that's why I have this. And the same thing for the columns, and then you can just do a topological sort. So I just made a function, topological sort, pretty straightforward. You don't have to use a queue. You can use any kind of data structure, because you don't really care about like the best order. You just care about a valid order. Yeah, like there are some problems that are like, how can you get through this the fastest, but you don't really care about that. So this can be a stack, a queue, whatever you want. And then basically, yeah, you have an order, you have a BFS, and then you just keep, for every single node that has 0 in degrees, you add it to your BFS initially. And then you just pop nodes from your BFS, either from the left or the right, doesn't matter. You add it to the order, and then you look at all the children, and you subtract in degrees for every child, because basically once you remove the parent, that edge gets removed, so you have less in degrees for the child. And then if that child in degrees goes to 0, now you can take that child as part of your path. And then you basically have to check, like, if you were able to do a complete topological sort, your length of this guy that you return should be k. And if there was a cycle or something, it'll be less than k. So if you got it to be k, that means you were able to get every node, and there is a valid row or column ordering depending on which one. If not, you can't do it, so you just return the empty array. Then you just make the result, and you make the column locations like I was talking about to get O of 1 indexing for columns instead of n squared. And then you just put all the column locations from the column order, and then you go through the row order, and you just say, okay, for the row order, my item, whatever's in that index, will go into that row, and then the column will come from the column locations. And then you just return. So there's definitely like more efficiencies you can make. I wasn't super concerned about that kind of stuff. So yeah, as far as runtime, I'm sure there's like better stuff. I guess we can look maybe using only arrays or something. I don't know. DAC. I guess less hash maps. Yeah, I think when I noticed in these Java solutions, the more hash maps you use, the slower it seems to go. I think ideally you want to just use arrays for everything if you can. Like no list, just arrays. They are like faster, I guess. So even though the big O complexity is the same. And yeah, I think this is like the best thing you can do. You can usually with topological sort, there are other solutions like BFS, DFS, or something. But knowing topological sort will make these things easier, I feel like, because the BFS and DFS can be tougher. And this is going to be pretty tough to do time complexity. I don't even know if it'll run it here. Probably won't, but let's see. So in my solution, I put every single number in the hash map, so that's O of k. And then also you have the row conditions and the column conditions. That's like, let's call that like R and C. So maybe like R plus C plus K, depending on whichever one's longer and stuff. Then the actual topological sort. Don't remember this off the top of my head, so let's figure this out. So you have a BFS, and basically every single node is going to need to be in the BFS. And then for every single node, you're going to cover the children. So I think that's going to be... So we're going through every single node, and we're going through every single edge. So I think that's like E plus V, which is, these are already included, right? These edges are already included. So I think the topological sort doesn't change complexity here. Yeah. And then the column location, so that's just going to be O of K. It's fine. This is going to be O of K as well. These row order and column order should both be length k if you were able to get a successful topological sort, so it doesn't matter. So yeah, I think it's just this. So the length of the row conditions, column conditions, and k. And I think, yeah, these can be a lot bigger than k. So space. Okay, so for the graph, like I said, you can have every single node, so that's k, and every single edge, so that's already, I guess, like the same kind of thing, because these are, I guess, both of these are edges. R and C are edges, and you have two graphs, so you're gonna have both. In degrees is gonna be O of k, so we already have that included. Column order, row orders, O of k. Call locations, O of k. BFS. You can only have each node once, so O of k. Order, O of k. Yeah, I think it's like this. Usually for graphs, it's going to be either like EV squared or some kind of thing, but the most common one is like E plus V, nodes plus edges. So I think it's like this. Yeah, so kind of a long one. The main thing to recognize is, yeah, learn topological sort and learn that once you get a valid row order and a valid column order, it's very easy to put items where they need to be. Just look where it is in your row and column order and put them there. And put one item per row, and then what the column is going to be where they are in the column order. Yeah, so if that was helpful, please like the video and subscribe to the channel, and I'll see you in the next one. Thanks for watching.